He was America's most trusted bridge engineer, consulted on projects worldwide. Yet Theodore Cooper never once visited the construction site of his greatest project, and that decision killed 75 men in under 15 seconds. Welcome to History Snapshots. This is the story of the Quebec Bridge disaster. Theodore Cooper was born in 1839 in New York, a time when bridge engineering was emerging as one of the most prestigious professions in America. By the 1880s, Cooper had built a reputation as the nation's foremost authority on cantilever bridge design. He'd worked under the legendary Eads on the St. Louis Bridge, consulted on dozens of railroad projects, and authored technical papers that became gospel for a generation of engineers. When the Quebec Bridge Company approached him in 1899 to design a span across the treacherous St. Lawrence River, it seemed the perfect capstone to a brilliant career. The bridge would be the longest cantilever span in the world, 1,800 feet between piers, shattering all previous records. It would connect Quebec City to the South Shore, opening trade routes and cementing Canada's industrial ambitions at the dawn of the 20th century. Cooper accepted the commission as consulting engineer, the most senior position on the project. But there was a problem that would prove fatal. At 60 years old, Cooper's health was failing. He suffered from chronic illness that made travel difficult, often painful. So he made a decision that seemed reasonable at the time. He would oversee the project from his office in New York, 600 miles from the construction site, relying on reports, telegrams, and photographs sent by the on-site engineers. It was a management structure that would have catastrophic consequences. The original design for the Quebec Bridge called for a main span of 1,600 feet. But in 1903, 4 years into planning, the Quebec Bridge Company made a fateful decision. They wanted to extend the span to 1,800 feet, making it not just the longest cantilever bridge in North America, but in the entire world. The reason was partly practical. A longer span meant fewer piers in the river, reducing construction costs in the brutal St. Lawrence currents. But it was also about prestige. Canada wanted a monument to rival anything America or Europe could build. Cooper agreed to the change. But here's where the mathematics became deadly. He didn't redesign the bridge from scratch. Instead, he modified the existing plans, adding length but keeping much of the original structural framework. The bridge would be built as a cantilever design, meaning each half would extend outward from the shore piers until they met in the middle. The weight would be carried by massive steel compression members in the lower chord, essentially giant metal beams that would bear the entire load of the structure as it grew outward over the water. Cooper calculated these members would need to support approximately 8,000 tons each. His specifications called for steel members weighing 58 pounds per foot. But as construction progressed, the Phoenix Bridge Company, contracted to fabricate and erect the steel, began making substitutions. Heavier materials were used. The actual weight per foot crept upward, first to 62 pounds, then 65, then higher still. Each change was documented in reports sent to Cooper's New York office. Each change increased the stress on the lower chord members, and each change brought the bridge closer to the mathematical threshold where steel stops bending and starts breaking. By 1907, the bridge was nearly complete on the south side, the cantilever arm extending 600 feet out over the river. Workers could see across to the North Pier. The finish line was in sight. In late August 1907, the on-site engineers began noticing something disturbing. The lower chord members, those massive compression beams carrying the bridge's weight, were bending, not dramatically, but visibly. On August 27th, Norman McClure, the Phoenix Bridge Company's inspector, measured the deflection. One beam had buckled outward by 2 inches. 2 inches doesn't sound like much, but in a steel structure, engineered to tolerances measured in fractions of inches, it was catastrophic. McClure immediately reported the deflection to Peter Slapka, the on-site chief engineer. Slapka was alarmed. He telegraphed Cooper in New York, describing the buckling and requesting instructions. Should they halt construction? Reinforce the members? Cooper's response was measured and, in hindsight, tragically insufficient. He acknowledged the concern, but suggested the deflection might have occurred during fabrication, not from structural stress. He did not order work stopped. He did not travel to Quebec to inspect the damage himself. On August 28th, Slapka sent another telegram, more urgent this time. The buckling was worsening. Workers on the bridge were becoming nervous. Some refused to go out on the span. But Cooper's reply didn't arrive until the following day. And by then, it was too late. What was happening, though no one fully understood it yet, was a phenomenon called compression failure. The lower cord members were being crushed by the weight of the bridge itself. Steel, for all its strength, behaves predictably under compression, up to a point. Beyond that point, it doesn't gradually weaken. It fails suddenly, catastrophically, like a soda can crushed underfoot. The Quebec Bridge had crossed that threshold. The mathematics that Cooper had relied upon, the calculations he'd made from his New York office without ever seeing the actual structure, were wrong. The bridge was going to fall. The only question was when. August 29th, 1907 was a Thursday, warm and clear. At 5:32 in the afternoon, 86 workers were on the bridge. Some were riveting steel beams. Others were positioning the next section of the cantilever arm, preparing to extend the span even further over the river. The sound came first. A sharp crack, like a gunshot, echoing across the water. Then, a groaning, wrenching noise as 19,000 tons of steel began to move. The southern cantilever arm, 600 feet of bridge extending out over the St. Lawrence, twisted sideways. The lower cord members, already buckled and overstressed, snapped. Without those compression beams to hold it up, the entire structure lost its integrity. Workers described the sensation as the ground disappearing beneath them. Men grabbed for railings, for beams, for anything solid. But there was nothing solid anymore. The bridge was collapsing. It fell in sections, the outer span first, then the sections closer to shore, each part dragging down the next in a cascading failure. Steel beams weighing tons apiece tumbled through the air. Rivets shot out like bullets. The noise was described by witnesses on shore as a sound like thunder, continuous and deafening, mixed with the screams of men. The entire collapse took approximately 15 seconds. 15 seconds for a structure 8 years in the making, designed to stand for a century, to disintegrate into a twisted mass of wreckage in the St. Lawrence River. When the dust settled, 75 men were dead. Some were killed instantly by falling steel. Others drowned, trapped beneath the wreckage in the river. A few survived by sheer chance, standing in sections of the bridge that remained partially intact, or thrown clear into the water and managing to swim to shore. 11 men were pulled from the wreckage alive. The rest were gone. Some bodies were never recovered, entombed forever in the steel grave at the bottom of the river. News of the disaster reached Theodore Cooper by telegram that evening in New York. His response, recorded in the official inquiry, was brief. "I am prostrated by this disaster." But prostration would not be enough. The world wanted answers. The Royal Commission of Inquiry into the Quebec Bridge disaster convened in September 1907, just weeks after the collapse. The commission interviewed dozens of witnesses, surviving workers, engineers from the Phoenix Bridge Company, inspectors, and Theodore Cooper himself. The testimony painted a damning picture. Cooper admitted he had never visited the construction site. He acknowledged receiving reports about the buckling lower cord members, but had not recognized the urgency. He defended his decision to extend the bridge span from 1,600 to 1,800 feet, insisting the calculations were sound. But the commission's engineers reviewed those calculations and found them fatally flawed. Cooper had underestimated the dead load, the weight of the bridge itself, by nearly 20%. He had used outdated stress formulas that didn't account for the behavior of steel under extreme compression. And critically, he had failed to implement adequate on-site oversight. The Commission's final report, published in 1908, was unsparing. It concluded that the collapse was caused by errors in design and lack of supervision. It specifically faulted Cooper for not visiting the site and for failing to halt construction when evidence of structural failure became apparent. The Phoenix Bridge Company was also blamed for substituting heavier materials without proper authorization and for inadequate inspection protocols. But the harshest judgment was reserved for Cooper. The report stated that as consulting engineer, he bore the heaviest responsibility for the disaster. His reputation, built over 4 decades, was destroyed overnight. He was 68 years old. He would never design another bridge, yet the story didn't end there. The Quebec Bridge still needed to be built. Canada's industrial ambitions hadn't died with those 75 workers. In 1908, the Canadian government took over the project, hiring new engineers and starting from scratch. The new design was more conservative, with heavier members and greater safety margins. But the bridge's troubled history wasn't finished. On September 11, 1916, as workers were lifting the central span into place, the final piece that would connect the two cantilever arms, the lifting apparatus failed. The 5,000-ton span fell into the river, killing 13 more workers. It was a different kind of failure, a construction accident rather than a design flaw, but it cemented the Quebec Bridge's reputation as cursed. The bridge was finally completed in 1917, a decade after the first collapse. It remains the longest cantilever bridge in the world, a title it has held for over a century. But it's a monument built on the bodies of 88 dead men. Theodore Cooper died in 1919, 2 years after the Quebec Bridge finally opened. He was 80 years old, his final years spent in obscurity and, one imagines, considerable guilt. History has not been kind to him. His name appears in engineering textbooks primarily as a cautionary tale, the man whose arrogance and miscalculation killed 75 people. But the legacy of the Quebec Bridge disaster extends far beyond one man's failure. In the immediate aftermath, engineering societies across North America and Europe began revising their standards for bridge design. The American Society of Civil Engineers established stricter requirements for on-site supervision. Load calculations were scrutinized and updated. The concept of factor of safety, designing structures to withstand far more stress than they would ever theoretically encounter, became standard practice. The Quebec Bridge disaster also accelerated the professionalization of engineering. Before 1907, engineers were largely self-taught or apprenticed, with no standardized licensing or oversight. The disaster provided ammunition for reformers who argued that engineering, like medicine or law, needed mandatory education, certification, and ethical codes. By the 1920s, most U.S. states and Canadian provinces had implemented professional engineering licenses. The Quebec Bridge itself stands today, still carrying traffic across the St. Lawrence River. It's a strange monument, a UNESCO World Heritage Site celebrated for its engineering achievement, yet forever marked by the men who died building it. There's a plaque on the bridge commemorating the workers killed in both collapses, but few travelers crossing it today know the full story. Perhaps that's fitting. Every bridge we cross, every structure we trust with our lives, is built on lessons learned from failures like Quebec. Theodore Cooper's ghost haunts every modern bridge code, every safety regulation, every engineer who double-checks calculations and insists on visiting the construction site. The 75 men who fell into the St. Lawrence River that August afternoon didn't die for nothing. They died because one man, brilliant but fallible, made mistakes. And because of those mistakes, the bridges we build today are safer. Not perfect. Engineering will never be perfect, but safer. That's the cold comfort of disaster. We learn or we repeat. The Quebec Bridge taught us to learn.